we consider a robot described by the state equation given here, where x1, x2 correspond to the position of the robot and x3 is its heading. In this exercise, we want to control this robot so that it follows a 8, so a path with a 8 shape. My robot is represented by this triangle, where here I have x1, x2, x3, and it is moving like this, and I can only control so using u, the derivative of the heading. I cannot control the speed. So after, what I want this this robot follows. So at the beginning it is initialized here, for instance, and I will want it to follow something which looks like a 8, like this. That is the goal of the exercise. So after some initialization, it will go to the 8 and follow the 8. To start the exercise, the first question asks me to so give me the expression of a vector field which which has a limit cycle corresponding to a circle of radius 1, and the rotation is counterclockwise. So I will first check this using Python. So the code is the following one. I first enter the expression here of a function f corresponding to going to R2 to R2, corresponding to the field I want to draw. So the field is represented here, and we can see that in this field, if I follow this field, I will obtain trajectory which converge counterclockwise to this disk for all initial conditions. I have different trajectory even if I start from inside the disk. So this disk has a radius equal to 1. To draw this, I will use the quiver function, and I will need first to build my gridding corresponding to all these points. So it is mx, my corresponding to 2 vectors. Then I build the matrices x1, x2. Then using phi given here and called here, I will build the values for each vectors represented by the smaller rows here. And thanks to quiver, I will be able to draw this vector field. So I can control here the sample between 2 points. They are given by 0.5 here. So if I want something more accurate, I can put, for instance, 0.1. And the scale going to -5 and 5 correspond to to the size of my grid. If I go to Python, which I start the program, and I am able to see here the vector field with the limit cycle I can guess. From this expression of the vector field, I want to find an expression for another vector field obtained from this one, but with a different center, a different radius, and the direction, so clockwise or counterclockwise, of the rotation can be different. So how to build this expression? So I will take this vector field, and what I want to do is to translate it, or to zoom on it, or to change the orientation. So it can be done by a symmetry. So to change the orientation, I will have to multiply by, let's say, axial symmetry. For instance, it can be this one. And the axial symmetry, like this, can correspond to a matrix. It is a linear transformation which corresponds to 1, 0, 0, minus 1. If I want to change the radius, I will have to make some kind of zoom on homothétie, and the transformation may be rho, 0, 0, rho, and so on. So what I want to do is to change the center and to translate by a vector c. I want to change the radius, and I want it now to be rho. And also I want to have a direction, so either direct, which corresponds to epsilon equal 1, or clockwise, which corresponds to epsilon equal minus 1. So the transformation in P1, P2. So why did I take P1, P2? Recall that the state vector of my robot will be x1, x2, x3, and the vector P corresponds to P1, P2. So P1, P2 correspond to x1, x2. So the transformation I want is the following: J of P equal to, so I take P first, I will change the orientation by this matrix 0, 0, 0, epsilon. So if epsilon equal to minus 1, then I will change the orientation of the rotation. To change the radius, I multiply by rho, 0, 0, rho. I will multiply by p, and to translate it by the vector c, I will add c. So I want this vector field follow this transformation, which is called an action. So recall that if I want the action G on the vector field phi0, I will obtain another vector phi, which is given by this operator. So G, it's an operator rho of phi0 of P. So recall that this operator is defined by as follows. It is the Jacobian of J with respect to P, composed by J minus 1. So this one is invertible. J is an homeomorphism, so it is smooth and invertible, and its inverse is also smooth. Of P multiplied, so here it's a multiplication, by phi0 composed by G minus 1 of P. So in my context, if I isolate P, I will obtain so these two matrices are easily invertible. And if I call this matrix D, I can write that D equal to rho 0, 0, rho epsilon. Easy to multiply. Then I obtain, since the derivative of J, which is affine, does not depend on its argument. So this one corresponds to D here, the derivative with respect to P. Multiply the same, and here the inverse is easily obtained. It is D minus 1 multiplied by P minus C, so obtained by isolating P in this expression. So here, sorry, multiplied by phi 0, so phi 0 here is here, and this corresponds to this. So when I will implement it with Python, I will do as follows. I will write Z equal D minus 1 multiplied by P minus C. So here it corresponds to Z. Then I will have a new variable phi of Z, phi 0 of Z, and then the whole vector corresponding to phi will be D multiplied by W. I took the same program as previously, so the definition of V0. I still have here the draw field, but the difference now is that I call previously I was calling phi 0. Now I will call phi, which corresponds to the transformation of phi 0, by a translation represented by C1, C2, a zoom or nomothétie corresponding to R. So here the center C is taken as 2, 0. R is taken as 2. And the direction epsilon is equal to 1. It means that I do not change the direction. So what I did here is D is given by the matrix R0, 0, R times epsilon. Then I modify, so this is the action of J to obtain phi is given as follows, as previously explained. I took Z equal D minus 1, so this is D minus 1, multiplied by P minus C. W corresponds to phi 0 of Z, and what I return is V is equal to D multiplied by W. So note that since here I use draw field, since x1, x2 correspond here to matrices which represent the gridding, and here a vector field for each point, a vector for each point of the gridding. Then when I will call phi on this gridding, I cannot use the matrix multiplication of Matplotlib, Instead, I will have to perform the multiplication by hand, and it is what I have done here, because this and this can be either float or real numbers, or also sampling on my grading, so matrices. So I go to Python. If I start my program, I obtain the vector field, so which has been translated by the vector C. The orientation is still in the direct trigonometric direction, so counterclockwise. If I want to go clockwise, I will have to replace epsilon by -1. Okay, so now it is clockwise. If I want to go on the left, here I will put, for instance, -2. So it means that C1 will make me moving on the left. Okay, so, and if now I want to change the radius here is 2, but if I want something bigger, I will put 4. Which is represented here. And if I want a field corresponding to phi0, I will have to put no translation, radius equal to 1, and epsilon equal to 1. And in this case, I will obtain the same as phi0 obtained previously. Question number 2. Propose a controller so that the robot follows clockwise a disk of radius rho equal to 2 with the center -2, 0. So if I look at the picture, the center should be 2, 0, and it is counterclockwise, so I will follow this picture. First, recall that the vector field I want to follow is phi equal to d multiply by phi0 of d minus 1 times p minus c, where p corresponds to x1, x2. Okay. The position of my robot. It was the question number 2. So I will consider as an error if I have my robot, which is here, with a heading corresponding to x3, and assume that phi is like this, and I want to follow phi. So I will take as an error the difference between the two angles. So the error will be denoted by y, and I want it to be equal to 0, of course, which corresponds to the difference between my heading and the angle of psi. So it corresponds to arctangent 2 of psi2, which depends on p, and phi1, which also depends on p. If I call this one b and this one a, so I will obtain that the derivative x3 x dot equal to x dot 3 minus, and I will have to compute the derivative of the arctangent 2 first with respect to the first argument and then to the second one, so with respect to A and then with respect to B, and it is minus B divided by A square plus B square, A dot, plus A divided by A square plus B square, B dot. So this corresponds to the derivative, partial derivative of arc tangent 2 of BA with respect to A, and this one the same, but with respect to B. So C, and this one corresponds to U. So here I can say that y dot is equal to U plus plus B A dot minus A B dot divided by A square plus B square. Okay, so now I will have to compute A dot and B dot. The expression of A dot and B dot. So I know it is the derivative of phi. And I have the expression for phi, which is given here. So I obtain that it is derivative respect to t of d multiplied by phi 0 composed with t minus 1 b minus c I can put out of the parentheses the d, and if I compute this, I obtain that it is d, so it is a composition of two functions, so I will obtain d multiplied by the partial derivative of p with respect to p, d minus 1 p minus c multiplied by the derivative with respect to t of what I have inside, so t minus 1 multiplied by p minus c. Okay, so I can also put this out of the parentheses, and then this is constant, so it will be removed, and this will correspond to t minus 1 multiplied by p dot. Okay, so now this corresponds to p, which is here, corresponds to x1, x2, and the p dot, which is here, corresponds to cos x3 sine x3, and I get this thanks to the state equation of my car. So I have an expression of a dot p dot that I can put inside here to have an expression of y. I also need to compute the derivative of phi 0, excuse me, here it's phi 0, with respect to p, and I have an expression given in the exercise of phi, and I obtain that the derivative of phi 0 with respect to p at point p is equal to minus 3 p1 square minus p2 square plus p1 minus 2 p1 p2 plus 1 minus 2 p1 p2 minus 1 minus 3 p2 square minus p1 square plus 1. So now I have an expression for y dot, and I have also an expression for y, which was given above here. And what I want now to obtain is an expression for u. So I will ask to have here y dot equal minus y. Why? If I ask this, then I know that y, if this, then y will converge to 0 in something like about 1 second. Okay, so I will ask to have this equal, so plus this one should be equal to 0. So if this one plus this one equal to 0, I will isolate u, and I will obtain u equal, so it will be minus y given here, and I will also have this part, which corresponds to minus b a dot a b dot divided by a square plus b square. So it means that if I take this controller, then y dot will be equal to minus 1, then y will converge to 0, then I will follow my vector field. So it is a feedback linearization method. Now, without changing the derivative, to avoid jumps between 0 and 2 pi, I will have to replay, to add here the classical sawtooth function. So it will not change the derivative, so it will not change the reasoning, but it will make me possible to avoid the jumps of 2 pi. This was the old program, and this is the new one. So this part, this function, and this function, and this one also exist at the top of the new program. So what I added? First, I added this initial state, minus 3, minus 2, minus 3, 1, so 1 for the heading, corresponding to the initial state of my robot. I also added a for loop from 0 to 50 with a sampling time of dt initialized here at 0.1, so a small one. The scale is always equal to 5. I initialize my matrix D with a radius r equal to 1 as previously, 2 and 0 for the center. I added a controller that has just been developed a few minutes ago. So what about the controller? The controller here generates the output u. So it is given by u. So recall that u computed here correspond to y minus ba dot minus ab dot divided by a square plus b square. It is what I have obtained before. But the error y was given by this error, this error here, -1, minus, so by this error, so it's here it corresponds to y. Now a and b are given by phi function, which is here, and dA dB are obtained thanks to the derivative of phi. Derivative of phi is here. So for this, this function corresponds to what I have called before the derivative of phi with respect to p. So for this, I use the expression I have obtained before, and I use here the Jacobian matrix of phi 0 at point P. If I run this program, I switch to Python, I obtain here my car going to the circle, so the initial condition was here, and converging to the limit cycle of the vector field. Question number 3. I consider two vector fields of a shape similar to the previous question, still represented here. I have to build an automaton with 4 states so that the robot is attracted by a cycle corresponding to an 8. And this is illustrated by this picture. This is the initial condition. First, I follow the first circle, and then the left circle, and I come back to the right circle, forming an 8 like this forever. So for this, I will build 2 sets, this one and this one, yellow. The first one we'll call Q1 is given by the equation is a set of P such as P2 larger than 1. So in fact what I have here is P2 here I have P1 and here I have 1. Okay, this is the first center and here is the second center, and recall that this radius is equal to 2 and this one also. Here I have, for this circle I have epsilon equal to 1, and here for the other one epsilon equal to -1. So how can I build the automata? I will consider 4 states. The first one will correspond to Q equal to 1. It means at first I'm going to follow the right circle. So I will present like this. Q equal 1 and I follow the right circle. Then once I am in Q1, so here, once I'm here, I switch to the other state corresponding, I will call it q equals 0. Here I will switch to q equal 1. It means that now I am in the red box. The transition is obtained as soon as I am in Q1. The other set, I will call it Q2, and correspond to the set of all P such as P2 is negative. So once I am in Q2, so I turn like this. Once I am Q2, it means I am here. Then I will switch to the state to follow the left circle. I will switch to Q equal to 2. So I will continue like this, and I will switch back to the other state. So Q equal to 3 as soon as I enter in Q1. And then again, once I enter in Q2, I will switch to Q equals 0. Okay. So here Q2. So it is the automata I propose, and it is important to understand that Q1 and Q2 have an empty intersection. So Q1 inter Q2 is equal to empty. But more than this, there exists a distance between the two of them. So it means that it is impossible to switch many times in a small interval of time between Q1 and Q2 due to this distance. And in case where I have some situation where Q1 and Q2 are have a distance which is non-zero, and it may happen that the switch may appear an infinite number of times in a small interval, and it is what we call a Zeno effect. So here the Zeno effect cannot appear. It means that I cannot switch from one state to another an infinite number of times. To program the automata with Python, I first initialize Q to 0. Okay, so it means that I start here at Q equals 0. Then I have 4 states. If Q equals 0, then I follow the circle on the right, and also for Q equal to 1, so here I follow the right circle. For Q equal to 2 and Q equal to 3, I follow the left circle. And I draw the robot with different colors for the simulation. So I take exactly the same program as before. So this one, I do not change anything here. I only change this part. Okay. But I added the automata. Then what happened? So the change of state is here. If Q equal to 0, so this is a modulo. So if Q equal to 0 or 2, so if I am here or if I am here, as soon as I am in Q1, so Q1, it means that x2 greater than 0.5, I said before 1, so I can put 1 also here, but it's very similar. Then I switch to the following state. It means I add 1 modulo 4, because I have to come back once I am to 3, I have to come back to 0. Moreover, if Q equal to 1 or 3, so if I am here or here, and if I enter in Q2 here, then I jump to the following state. So that the way I program the automaton. I switch to Python. This is my program. I run it. So I am blue at the beginning because q equals 0. Then red, q equal to 1. Q equal to 2. And q equal to 3. And I will come back to q equals 0. And my car performs the 8th circuit forever.